Welcome back to Grokking Artificial Intelligence of Things. This is actually module 2, part 2 on the connectivity of AIoT. So the first thing that I actually want to talk about is this idea about the different protocols. So I actually have some references here, which I hope you can refer to take a look at some of these possible additional protocols that on top of what I have was already mentioned earlier. But we will go into the details of this later on. Just go into each of these pages to show you what it has. Okay, so from the first link, which is the Postscapes link, this is actually a well-known website containing a lot of useful information for IoT. And you can see that there's a list of the different protocols that I'll be talking about and have already mentioned some of them earlier as well. So do take a look at this. There are some of the protocols that I have not actually included in the slides, but the details can be actually found from the links that I have provided here. Okay, so this one good resource site, and this table actually is quite useful. So we'll be talking more about the different types of wireless technologies that we'll be using for AIoT. So this particular table, I'll talk about it in more detail afterwards. So the other link is actually the JSON for linking data. So I've already mentioned the data format known as JSON, and also the binary versions, CBOR and Bison. But this is an additional version of JSON that has actually been implemented to take into account that data that you have may be linked to other data on the internet. That means the information that's actually being stored at what or being created at one location may be referencing information that's actually related to it at some other location, what we call linked data. So it's an enhancement of the JSON format. So you can see that there's the addition of some text that's focused on the URL or the hyperlink. This is especially useful for data that is related to the Web of Things, which we're looking at later on in this module. So next we'll be looking at the impact of the different wireless technologies that we would want to use in the AIoT network. So the first one is actually 5G. 5G is actually a new wide area cellular network that's being introduced around the world. It has actually a number of tremendous effect for IoT and AIoT especially, because first of all, you can find that actually the bandwidth is much larger, is much faster. It's like 10 times, up to 10 times or 100 times improvement over 4G networks. So that's in terms of the speed of the connection. So for AIoT, as mentioned in the first module, it does tend to actually transmit and receive more data than basic IoT devices. So that improvement in the transmission speed definitely helps. The other thing that is useful about it is actually this other aspect, which a very low latency, which I've already mentioned before earlier, that low latency is associated with more stability when you try to control things. So the idea behind AIoT really is to automate or remove humans from the control loop. So when the information has been processed after it's been read in from the various sensors on the net, large latency when we try to control it with some sort of actuator leads to instability in the control. That means you tend to overcompensate. So by the time you want to steer left, the car has already traveled very much further to the right than you had originally sensed earlier. So that delay between your sensing and your reaction is going to lead to instability. So by cutting down the latency from what we typically find in the internet network or even in a mobile broadband in the 4G era to 1 millisecond, it really does help to improve the stability of the control. So things like remote operation, teleoperations, controlling robots from a remote location, they are only possible when we can cut down the latency to this. And just to give you an indication about how fast this actually is, a typical human reaction time between when you see something and when you actually react to it is something like 200 milliseconds. So that is actually what we are observing here is actually 200 times faster than your human reaction speed. I mean, that's if you have been trained. Of course, if you're like me, maybe my reaction speed would definitely be more than 200 milliseconds. That's talking about the very good person has already been trained to respond very quickly to something. It tends to be only as low as around 200 milliseconds and not fast any faster than that. So this is really super duper fast. Right, and the last one, which is actually useful for oftentimes forgotten, is that actually for a 5G network, it has a much higher density in terms of device capacity. So even for a wireless LAN environment, there's only that many laptops or wireless Wi-Fi devices that you can actually put within a square meter where there's wireless access. So that's fine if you're talking about humans being using it, because you can't pack that many humans into a given square area. However, when you talk about devices, the density can be much larger. So having that ability to pack in a lot of transmitting and receiving devices within a small square area really helps. And actually, this is actually one of the advantages of 5G, besides the faster transmissions and low latency that would be very useful in the IoT environment. Because if the IoT devices are very simple, you can pack a lot of them within a small square area. And the last one is that narrowband IoT, which we'll talk about afterwards, is a kind of a radio protocol within the 5G network. That actually allows you to transmit at lower rates within the IoT network, but you transmit it using a much lower power consumption. So you can see that we can actually achieve lower battery life with 5G technology. It is not, it's maybe a bit misleading, but basically for this lower power transmission is also associated with just using a smaller fraction of the total value. You can't be expecting it transmitting at 10 gigabit per second and have a 10-year battery life. That's not the case, but it's just that the 5G network can support a wide range of users. So if you need faster speeds, you can do it with low latency, but of course your power consumption will go up. But if you don't really need that 10 gigabits of speed, you just want to power your IoT device for a long time, you do not need to switch to a different network. You can still be within the 5G environment, transmit at a lower speed with the corresponding improvement in the power consumption, so you can stretch the battery life. So this is actually just shows you that the 5G technology is actually pretty flexible. So you have a possibility of a wide range of different use cases being accommodated without you having to switch to a different radio or different network technology. So this is also another slide just showing you the wide range of use cases for the 5G network. So you can find that narrowband IoT protocol, which is actually part and parcel of the 4G, 3G, as well as the 5G networks. It will remain as part of the 5G network. So even though we are using 5G new radio as a radio access network, we will still be able to access the narrowband service, which is the one I mentioned, a low transmission speed, but you are able to transmit large, you can accommodate many devices, but you are able to transmit also at very low energy, because things like smart metering, you really don't need to have very high bandwidth, but you do really need to because it's a small data volume, so don't need very high bandwidth, but you do want the device to be able to last very long in terms of the power consumption. Okay, things like tags to manage your physical assets. So these are just radio tags attached to your physical asset devices, so we can actually monitor their condition. Again, don't really need much in terms of the transmission of data, just the location and ID of these devices and maybe some simple parameters for them. For more complex situations, you can see that, for example, the asset that you're actually measuring is actually moving around and it has some amount of complexity, for example, vehicles. Then you will need higher throughput because you might actually want to monitor things like the dash cam of the vehicle to see whether the driver is actually driving safely, obeying all the traffic rules. And you want low latency so that you're able to send back control to the vehicle itself. And you do expect the volume of data to be larger. So it could be including camera output or camera input and being sent back to the back end for monitoring purpose. So things like 5G, which has a high bandwidth, low latency, really would come into useful here, especially to control robotic devices like drones. So if you're trying to control a drone from remote, you have to make sure that your camera that you can observe from the drone and the control signal you send back to the drone is all occurring within a very low latency, right? Because if you have high latency, it might lead to instability. So beyond the horizon, beyond visual sight flying of drones, this is actually one of the application areas that 5G would make capable. So most drones, the normal drones, you have to have line of sight to actually look at the drone where it is, and then actually fly the drone while it is within your view. But for applications like maritime applications or larger areas surveying, you really want to have the drone capable of actually being out of your line of sight. You can't really see the drone, but you can see what the drone sees using a camera feed from the drone. So I believe this is actually being piloted in Singapore right now, where they are sending out drones to see beyond the range of what you can see on the shore. Right, so 5G actually makes this possible because it can cover the area, and when I want to control the drone, I can still be sure that my control signals that I send to the drone are actually able to be read and affected without causing instability in my control. As mentioned before, delay in the control loop just leads to instability in the control system. Autonomous vehicles, autonomous aerial vehicles, that means they have some amount of self-piloting capability, but the control may be actually done in the cloud. That means it's not fully self-piloting in the sense that everything is just remotely controlled on the drone itself. So some amount of planning may be done in the back end rather than relying on the more limited compute resources we have on the UAV. So in this case, some of the AI processing is done on the device itself, but some of it is done on the back end. So for this case, just like before, we need to have low latency, right? So that the control loop does not take too long. The delay is reduced. Now, other applications for 5G include entertainment type applications. So you can see here, VR, AR definitely uses very large bandwidth to support multiple video channels so that you can achieve the VR effect. So for other robotic type controls like autonomous vehicles and even train control of a train that doesn't have a driver inside, right? It's an autonomous or remotely driven train, like the ones that we have here in Singapore as well on the Northeast line. Then this low latency is also going to be helpful for it. And on top of that, very high reliability that we find if you use the 5G NR. 5G NR is actually the official endorsed so-called 5G radio access protocol. During the migration process, there are some operators that roll out 5G, but without using the new radio. That means they actually operate at a lower speed, but they try to migrate from the existing infrastructure that they have for LTE or 4G advanced networks. So the true radio protocol for 5G is actually 5G NR, right? Which is the so-called the standard version, not the pre-standard version of 5G. So we have other applications like smart grid, etc., etc. So in the industrial automation context, 5G network you can actually control your robots from remote, as well as collect your metering information from these robots using the 5G network. It supports those kind of use cases. So this is just a table showing the range of different applications and the different types of radio access. So in today's context, there are many different radio technologies available. So the important thing is to note that how far do you need to transmit the range, because for some applications, if you are going to be needing to transmit into the cloud, for example, IoT applications, and your training for your machine learning model, which we'll talk more about in module 3, is actually done in the cloud because you need higher computer resources, then your transmission has to be longer range. However, you can also have a two-step approach. So you gather the information together using all these more local radio technologies where the distance is short, but the gateway that gathers the information will then transmit that information to either over the broadband or over one of these longer range transmission technologies like 5G back to the network, right, back to the cloud provider. So it can be a direct connection. That means if I have a device that has already remotely fielded, maybe a drone flying around over the sea, and I want to send back the information back to the cloud, and then I would use 5G directly. But if I have a factory environment and I don't want to attach a 5G to every single one of my factory equipment, then what most people would do is that they will use Wi-Fi or Bluetooth to collect the information to the gateway, and then from the gateway, it then sends it out to the remote end using a more long distance transmission like 5G or LoRaWAN. Okay, LoRaWAN stands for low energy, long range, wide area network. So this is the kind of technology is using, as mentioned here, radio bands that were previously used by the very old mobile phones and also GSM. Most of these bands have become freed up because with new mobile technologies like 3G and 4G, these bands are no longer in use actually. So freeing up, moving away from 2G really would free up quite a bit of bandwidth for other applications. Right, the other thing that we would actually want to consider is the power requirements. So for for many devices, we do not want it to be having a permanent supply connected to the grid, or it's not possible to permanently supply it from the grid. So we need to have very low power transmission so that the batteries that we put on the device do not have to be replaced very frequently. So this is actually the case where we want to use technologies like Bluetooth, low energy. It's not really that slow, but in terms of power transmission, it's actually very low. So this is another diagram just to show you that actually depending on application area, the range and the power, there's a trade-off. So some technologies focus on low power, but the range is more limited. Other technologies focus on long range, but the power is low, is higher. And long range and high and low power basically means that you must cut the transmission rate. You cannot have long range, low power, and fast speed at the same time. So one of the three have to be reduced in order to meet this. But so you can see that because of different requirements in different sectors, right, you will find that we have many different radio standards being adopted. Some of them are just industry standards. It's not an international standard. Right, so this is another diagram to show you the range. So you can see that long range, high power, very high power, you have 5G, but the speed is also very fast, but the power consumption and the cost is high. Whereas for things like RFID, it's a very low range, power consumption is also fairly low, but the speed is very, very low. Bluetooth low energy is something like in the middle range, whereas Wi-Fi is shorter distance, high speed, but the cost is similar, almost the same. In terms of power consumption, is actually in the range of what you can see in 3G, but not maybe as high because you don't need to transmit it over such a long distance. And the cost here is not so much dollars, but the cost in terms of the transmission power required. Okay, so you can see here another range, so there are actually new standards coming, new proposals coming out, just like the LoRaWAN. So there's this one that extends the range of some of the wireless Wi-Fi technologies. So there's this Wi-Fi Sun Alliance. So this is actually a medium range protocol. So power is in the medium range, but it's not super fast, right? As compared with 5G. So you can see the difference in the transmission speed. Right, let's move on to, so this is a reference that you can just go to it. So Cisco is actually one of the members of this alliance. Okay, there are actually many different protocols, which I'll talk more about later on. But just to have a high level overview of this. So here, if you have a web of things, you can see that they will actually write over different protocols. So the web of things actually can be used over HTTP type networks, or it can be using one of these other more IoT specific protocols. But I will describe what these are in the next video. So you can see that there's a difference between the IoT stack and what we can normally see in the web stack. So in terms of data format, I've shown you this diagram before. In the web, we have HTML, XML, JSON, but in IoT, we try to use binary to reduce the amount of space occupied by the data. And then instead of HTTP, we'll be using some of the other protocols that was mentioned just now, MQTT, the very exotic sounding acronyms, and the CoAP, which is a constrained application protocol. So they can run over more limited devices and doesn't take up so much computational resource. TCP is harder to implement with a simple networking stack. So many of these constrained protocols, they just run directly over UDP, which is a much simpler protocol. So you can see the difference between these. So there's MQTT is actually one of the most commonly used protocols, and I'll talk a little bit more about this afterwards. L2WM, you can see that there are alternatives that people have proposed to the MQTT. Okay, so this is actually a broad overview about the different protocols, and you can see some of them can write over TCP, CoAP, where you have more constraint, will write over UDP. And in the Web of Things environment, using the idea for Web of Things is to use the World Wide Web protocols to do the transmission rather than using a new protocol. So we use the traditional stack that we find in the web, but we have a new use case for it. And you find that actually it may not be so far-fetched because for the AIoT devices, at least, the more capable devices, they already have an embedded Linux kernel typically, and TCP, HTTP would already be present for this type of devices. So for the more basic IoT devices, I think you would need all these exotic protocols. But for more AIoT, actually, it's quite possible that this is going to be just make sense for those devices because they already have the built-in capability within the operating system anyway. So this is actually the other things about it. So in terms of the security features, many of them use the substandard SSL security layer where it's available. It makes sense, especially for the Web of Things environment where you're transmitting over HTTP protocols. We just use SSL, which is the standard way of implementing a secure connection for HTTP. You would observe this whenever you're using HTTPS instead of HTTP in the URL. So because of the many security concerns related to the World Wide Web, actually it's fairly standard that most websites will just default to HTTPS now, right? And the browser will typically give you a warning if it's still using HTTP. That's when HTTPS is in use. Basically, the underlying secure connection layer is the SSL. However, SSL, just like HTTP, does take up quite a bit of resource to actually implement on the device itself. Not a problem if you're running a more capable device like something that can support AIoT. But if you are working with a more constrained IoT device, like the ones that can only run UDP and CoAP, then they would not use SSL, but they will use a simpler transport security layer called DTLS. Right, so you can look this up, DTLS. There are many references for it, but this is actually something that would go with the CoAP protocol stack rather than the ones that are using TCP and running on a more capable device. Mid-range devices are more also likely to have this capability built in. Right, so the other thing is the sponsoring organizations. So you can see that different organizations, they focus on different aspects. So folks like Oasis as one standards organization, the Internet Engineering Task Force or IETF, they have proposed different ones as well. Then even the mobile, Open Mobile Group, OMG, have their own protocol called the DDS. So we can see that actually in the IoT space, because of the different radio technologies, and the different radio technologies have an underlying reason for it, is because of the very wide range of use cases, right? We can't be transmitting very fast, long distance, and at low power at the same time. So something has to give. So for different radio technologies, they focus on different things. So some focus on long range transmission, but high power and with high speed, right? Such as the 5G networks. Others focus on lower speed, but smaller range, but also much lower power requirements. And the different protocols actually correspond to these different underlying physical layers that we see in the radio transmission network. So if it is already meant for a more constrained environment, I'm transmitting low speed over a short range with low power, then it doesn't make sense to use something like a Wi-Fi type protocol stack or internet protocol stack with a full HTTP secure socket layer and full TCP as well over a very constrained radio protocol network like BLE, Bluetooth Low Energy, or even simpler than that, some 802 15.4 packet radio. This is a small machine-to-machine transmission network that's actually being defined by the IEEE. It's like Wi-Fi, but it's meant for very low, much lower speed, but shorter range, lower power. So there's this kind of technology, like, and that is actually being adopted by things like Zigbee. So because of this, there's fragmentation, right? Because of the different use cases, there's actually different communication protocols being used for them. It's not really going to be possible to fit in the full protocol stack for every single case. That's the underlying reason. So 6LoWPAN is the one that mentions now. It's a Wi-Fi type network that has low power, shorter range, but using low energy, but they don't support such a large transmission rate. Others for telemetry, that means they're actually just doing sensors data. They may also transmit at very low power, but over a longer range. Right? This, as you can find, this security layer, the DTLS is not as heavy as the SSL, so it's going to be used for these constrained devices like the CoAP stack would be used for this as well. And we actually come to the end of this portion. So just repeat that, summarize some of the findings that we have for this part. So as compared with maybe 10 years ago, the range of wireless technologies has expanded a lot. we do really find a big range of different wireless technologies now. Low power, limited range, right? But the speed is low, or all the way to high power, high speed, but using a much larger amount of battery power as compared with your other networks. And of course, sometimes we just want to gather lots of data within a short time, within a shorter area. So like things like Wi-Fi can be used at the gateway level so that we can actually collect the data at a central point and then transmit it using a more long-range transmission technology like 5G. So this is one challenge. So the other challenge, of course, for these different radio technologies, actually the density is different. How many devices you can squeeze within per square area is quite different. So things like Bluetooth is actually not intended for very, very dense deployment, right? The Bluetooth network can only support a limited number of devices within a square area, whereas things like Zigbee and even NB IoT, they can actually support a much higher density. So what's not present in this diagram, which is just comparing power, data rate, and nominal range, is also the device density, which is the fourth dimension, right? So if you would like to have an interesting exercise, I would really suggest you try to also find information for the last dimension for each of these protocols. Google is a friend. I'm sure you can find it. So another row to just compare the device density that you can have per square meter for any of these technologies. And you find that actually for most of them, actually it is not very high. Because most of these radio technologies and standards were designed for an age that IoT was not really the predominant user. So most of these radio networks were originally designed for the internet of humans. So in terms of human usage, we don't really need that high density because we can't squeeze that many humans into a room. But when it comes to devices, obviously you can squeeze a whole lot of devices within a room. So yes, this will be a very interesting fourth dimension that has not been considered by many of these technologies. So, they do not put it in here, I think mainly also not to give you some discouragement to use any of the other technologies, but definitely it is a constraint that you should be aware of when you're trying to deploy this in real life, in a real project or real environment, because the device density definitely affects it. So like, for example, on a factory floor, how many sensors you can deploy for your manufacturing cell, it will depend on the radio technology that you employ, right? If you cannot deploy that many sensors, then you can only have that limited number of readings that you can have within that manufacturing cell. Right. Okay, thank you very much. And I will see you in the next set of slides for the part 3. Just stop this.